You know, in machine learning, we often have this picture of a single super smart model making all the predictions. But what if a whole team of models could actually do a better job? Today, we're diving into one of the most powerful concepts out there, ensemble methods, where combining models leads to way smarter and much more reliable predictions.
All right, so here's what we're going to tackle. First, we'll quickly look at why a single model just doesn't cut it. Then, we'll get into 3 powerhouse strategies: bagging, boosting, and stacking. And finally, we'll figure out how to choose the right one for the job.
So why do we even need a team in the first place? Well, it's because any single model, no matter how sophisticated it is, tends to struggle with 2 big problems: bias and variance. And trust me, getting that balance right is the name of the game. Let me put it this way. A high bias model, that's kind of like a student who barely skimmed the textbook. It underlearns, so it misses all the important details. Then you've got the other extreme, a high variance model. This is the student who memorized every single word, every comma, but can't apply any of it to a new question. It overlearns the training data so much that it's useless on anything it hasn't seen before.
Okay, so if one model alone has these blind spots, what's the fix? You guessed it, teamwork. This is exactly where ensemble learning makes its grand entrance.
The core idea here is actually pretty simple, but it is incredibly powerful. It's this idea that the collective wisdom of a diverse group is just plain better than the opinion of a single expert. So instead of banking on one model that might be flawed, we combine a bunch of weak learners to create one ridiculously powerful, strong learner.
All right, first up is a strategy called bagging. And honestly, the best way to think about it is like a democracy for models, where every single opinion gets an equal vote.
So, bagging is short for Bootstrap aggregation. Now, that sounds a little intimidating, but the key word here is bootstrap. All it really means is that we're creating a ton of random, smaller datasets from our main data. Each model gets trained on a slightly different view of the world, which gives it a unique perspective.
And the process itself? Super simple, really. First, we whip up those random data subsets. Then, we train a whole bunch of models, say a forest of decision trees, all at the same time, in parallel. Finally, we just bring all their predictions together and let them vote. For a classification problem, the majority wins. For a regression problem, we just average their answers. Simple as that.
So, what's the big idea with bagging? What's its main job? It's all about one thing: reducing variance. See, by averaging out the predictions from all these slightly different models, their individual mistakes tend to cancel each other out. This gives you a final prediction that's way more stable and much less likely to overfit. The most famous example of this: the random forest algorithm.
Okay, so if bagging is like a democracy, our next strategy, boosting, is completely different. Think of it more like a mentorship program, where each expert trains the next one in line.
Yeah, unlike bagging, where everyone works at the same time, in boosting, the models are trained one after the other. It's sequential, and each new model has a very specific job: fix the mistakes of the model that came right before it.
You could almost picture it, right? We start with a pretty simple base model. Then we look at everything it got wrong, and we tell the next model, hey, you, pay extra special attention to these tough ones. This cycle repeats, and you end up with this chain of specialists, each one getting better and better at solving the problem.
So, while bagging was all about variance, boosting's #1 goal is to crush bias. By focusing like a laser on the examples that are the hardest to get right, the final combined model becomes incredibly accurate and far less likely to underfit. Algorithms like gradient boosting and AdaBoost are the rock stars of this technique.
All right, we've had our democracy with bagging and our mentorship with boosting. So what's left? Well, now we bring in the expert manager. That's stacking. This is the one who knows exactly how to use everyone's strengths to get the best possible outcome.
Okay, this is where it gets seriously cool. Instead of just a simple vote or some weighted average, stacking actually trains a brand new model. We call it a meta model, whose only job is to learn how to best combine the predictions from all the other models. It's a model on top of models.
And the real magic of stacking is diversity. We're not just using a bunch of the same kind of model. No way. We can have a team of all-stars, maybe a decision tree, a support vector machine, and a neural network. They all make their own predictions, and then those predictions get fed as input to that final meta model, who looks at what the expert said and makes the ultimate call.
So because it's so smart about combining the strengths of different types of models, stacking is an absolute beast at tackling both bias and variance. This is why you see it pop up all the time in machine learning competitions. It's often the secret sauce to winning. All right, so now we've met the whole team: bagging, boosting, and stacking. The big question is, how do you know which one to pick for your problem? Let's get into the practical side of things.
This little chart here really lays it all out nicely. Just look at that approach row. Bagging is parallel. You can train everything at once, which is awesome for saving time. But boosting, that's sequential. You gotta wait. And then there's stacking, which is hierarchical, bringing together different models to hit both bias and variance. It's all about picking the right tool for the job.
But is all this extra work worth it? I mean, just look at this chart. The answer is a huge yes. Going from just one model to an ensemble like bagging or boosting gives you a huge jump in accuracy. But then stacking comes in, and by being so clever, it can often push that performance even higher.
And don't think for a second this is just for old-school models. Oh no, these ideas are absolutely fundamental in modern deep learning. Just imagine training several totally different neural networks. Maybe one is great at seeing textures, another is a pro at recognizing shapes. By stacking them, you can get state-of-the-art results in super complex fields like medical imaging or self-driving cars. Sure, it takes a ton of computing power, but when you absolutely need the best, most reliable result, building a deep ensemble is how you win.
So that really brings us to the big takeaway here. We've seen how combining models, whether they're voting or mentoring each other or reporting to a super smart manager model, creates this incredible predictive power. It just goes to show that in machine learning, just like with people, the team is almost always stronger than any single superstar, which really makes you wonder, what's the next huge problem this wisdom of the machine crowd is going to solve for us?